My name is Robert Panas. I'm a research engineer in the Materials Engineering Division. I've been working on MEMS micro devices and novel microstructures. I was studying in grad school at MIT. Ended up having one of my peers from my MIT laboratory got a postdoc at Lawrence Livermore. And we were talking about possible ideas, things that he could propose, and stumbled on the idea of starting to build a better micromirror design. At the time, we thought, wouldn't this be great for 3D TVs? And we ended up pushing that for a while, only to find out that Livermore is not necessarily the place to be developing 3D display technologies. There were much better ways that we could help, and the idea kind of picked up a momentum of its own. So we've built a precision beam steering on a chip technology. Very compact, very fast capability to point beams exactly where we want them and cancel out vibrations to create very clean images. The area that the mirrors were originally developed for was for NIF, to see if we couldn't build large aperture arrays, so very large numbers of mirror in these fractions of a meter almost sized diameter scales, where it's completely coated with these small millimeter mirrors. Use those to fix wavefronts for the NIF lasers. That turns out to require several generations more development for us to reach the point of these 10 or 100,000 mirror arrays. In the meantime, as we brought the technology online, we've realized there's a whole host of other places that we can help. Is that even a few mirrors end up being very critical for things like stabilizing beams in precision optical systems, or helping give us this sort of precision high-speed steering that LIDAR, it turns out, can draw on to produce this next-gen very compact LIDAR unit. The place where we're finding that there is a lot of value to what we're doing is just solving this present challenge of how do we get sensing into these vehicles so that they can understand their environments as well, if not better, than how people understand their surrounding environments. There's a great difficulty between these algorithms that can interpret all the images, but collecting. There's a gulf between the world around them and the algorithms that can do all that work of calculating, predicting trajectories, understanding how to move the car. And there's a number of different technologies that are being thrown in to that gap to try to solve it, whether it's radar, whether it's cameras and LIDAR units, ultrasound. It looks like the answer to give these vehicles the kind of situational awareness that they need is a combination of all of these. And LIDAR plays a key role to act like a camera to collect 2D images, but also with distance on those attached to each point on the image. So the autonomous vehicle can very quickly sense the location and the type, the structure, the layout, or even the shape of any particular vehicle around it within its field of view, whether it's ahead of it, behind it, to the side. I think of it, LIDAR as not the only player, but a key player in ensuring that autonomous vehicles can really fully understand their environment. So I was fortunate enough when I joined the group to join into the Additive Manufacturing initiative. Additive Manufacturing jumped on the scene with the capability to produce these really advanced, very complex 3D forms. And we realized that we sat at just the right spot to take those advances that the lab was developing, that industry was developing, bring those into the microfabrication domain that we knew well, link them together so we could get the benefits of microfab, this precision silicon features, that very high speed, very fine features, with just a few critical components that we make in true 3D that allow us to create exactly the linkages we need to get the high kind of performance, the high performance needed for these MEMS micromirror arrays. So there's about a team of about 6 of us now that are developing the technology for all the way from creating the MEMS systems in conjunction with AM Fitzgerald, our MEMS partner, to assembling the systems, to testing them and building the control loops that let us drive the mirrors to do exactly the kind of high performance operation we want. So in about 3 to 5 years, we're hoping to have this technology fully matured, through the point of having the demonstration prototypes out, have those integrated into LIDAR companies' units, and be commercially producing MEMS mirrors for LIDAR units, for precision beam steering capabilities, for laser comms. We want to get this technology out and use, get it out to the world for use here. Rather than having this sit around on a shelf somewhere, we see a lot of possible advances that can be made by putting precision beam steering into developing systems from drones to autonomous vehicles. So we're very hopeful that we can help be part of that advancing those technologies.